In this video, I'm going to introduce the crossbeam-epoch crate, which is the de facto standard Rust concurrency library that is widely deployed in many products, including Firefox. So crossbeam-epoch is a faithful implementation of epoch-based reclamation. And so if you already saw the videos on the header pointers and epoch-based reclamation, I believe it is easy to understand the library's documentation and implementation. And also the docs.rs here, it contains all the documentation for this crate. So you can go there and read the document here. And it not only describes the implementation details of the library, but it also explains the APIs and also a little bit about the algorithmic details of these epochs. So please go there and read the document. And for example, it provides the APIs. For example, here you can click the things there, and you can read the APIs of Atomic and its APIs, functions, and examples. So we are going to look at the examples and what's going on there. But for now, let's just recognize that there's a documentation that contains the examples for each functions. And there are guards, for example, there are pin and atomic and shared, and they are the main API of the crossbeam-epoch library. So please read carefully about shared, atomic, guard, and pin. And it has been created in 2015 by Aaron Tiron, and so its age is 6 years old library now. And Aaron started this project to provide a very nice library for the garbage collection for concurrent programming. And I strongly encourage you to this document as well. So it not only implements the garbage collection algorithm, the epoch-based reclamation algorithm, but this library also provides an API that mandates you to use this library safely. And it explains a little bit about this effort in this section. And also in the previous section, it also describes the algorithm of epoch-based reclamation a little bit. So you can compare this document and the video I just created before and see what's going on there. And as I said, this Rust API is mandating you to use this API safely. So as a result, it created guard and pin and what is called owned and shared at atomic, and they are the fundamental APIs for the crossbeam. And in order to do your homework 5 and 6, I believe you need to master the API and list. So I strongly encourage you to this document as well. And after reading these two documents, you can now understand what's going on in the examples. So this is the stack implementation that is in the repository, our repository here. So in the remaining of this video, we assume that you already read the document and the crate and the document of Aaron. And now in the remaining of this video, we are going to read the implementations of concurrent stack, queue, and list once again, and then see what's going on regarding the garbage collection. So this is the stack implementation, and it has a list. It is basically a list of nodes, and in the push operation, there is no need to think about the the garbage collection, because we are not removing any nodes from the linked list, and we are not deallocating anything. We just create a new one, and then it is going to be it is going to be prepended to the linked list and so. And here still there's an interesting aspect regarding crossbeam. You create an owned pointer that is basically creating an object in the heap, but it is exclusively owned by myself and it is not shared by the other threads at all. That's the reason why this type is called owned. It's an owned pointer to the heap. So far so good, and we try to perform a CAS on the head. So we are replacing the head pointer with the original from the original one to the new node here, and that is just created before. And what is interesting is that the ownership of this newly created pointer is transferred to this function. So this function accepts and receives the ownership of the new pointer. And if this CAS is successful, then we are done. And if this CAS is unsuccessful, what is interesting here is that the ownership of the pointer you just turned in here, it is returned as e.new. As a result, in order to use this e.new, the new pointer, in the next iteration of this loop, you need to save the ownership of this to the variable that is meant to hold the ownership of the new pointer. So remember that the ownership to a heap object is created here by actually allocating an object in the heap, and this ownership is transferred here, and it is returned back when the CAS operation is unsuccessful. And if it were successful, then ownership is effectively transferred to the shared memory. So we don't need to care. You don't need to care more about the ownership of the object on your own. And interesting things will happen in the pop function. In the pop function, you are going to read some pointers, and finally you perform a CAS on the head pointer. You perform a CAS on the head pointer and replace the original head to the next pointer. It effectively removes or detaches the original head pointer from the linked list. And as a result, we want to free this node, but as we discussed in the previous video, we cannot do that without care. We need to retire this node instead of immediately freeing the node. And this defer destroy is basically the synonymous name of the retire. We defer the destroy of this using the guard. So that is basically the first, the second change we made to the example in the previous video. And I said that we need to delimit the codes where the thread is accessing the shared memory, and it is delimited by this pin function and the drop of this pin, the guard here. So effectively, an active state begins when you pin the guard here, and the active state is finished when this guard is deallocated, probably at this line. At this line, the guard is dropped, and when the guard is dropped, the active state is automatically finished. So you can think of this API as a wrapper around setActive and setQuescent function that guarantees that once an active state is created, and it must be somehow inactivated at some later point of time. So this is an RAII type wrapper around the setActive and setQuescent function, basically. And what is interesting about here is that this retire function is a method of this guard. And as a result, this defer destroy must be called inside the active state because it is a method of a guard which is existing only inside an active state, thanks to the RAI type API of this guard. So here is the active state, and this guard proves that at line 76 we are in an active state because we have a reference to the guard. So that is basically ensuring that retire function is called only inside the active state. Furthermore, these compare and swap and load functions are given a reference to the guard, which also proves that this reading the global memory is executed only inside an active state. The fact is guaranteed by the fact that the functions are given a pointer to the guard, which proves that we are inside an active state. The same thing happens in this push function as well. I mean, we are creating a guard here, and we don't need a guard at this point of time because we are just creating a new node inside a heap, and it is not accessing the shared memory. Until here, this N is exclusively owned by myself, so we don't need to pin the guard before the creation of this new node. And after creating this, after pinning the guard here, we can safely read the pointers because they are effectively protected by the epoch-based reclamation implementation. And what is interesting about this store function is that unlike load and compare and swap, it doesn't accept the guard function because we are not actively creating a new reference to the shared memory, so we don't need to be given a guard when the store is executed. If you have a pointer here, head pointer here, and this head pointer is effectively annotated with the scope of the guard, which is the duration of an active state, and that proves that the store function is executed inside an active state. So that's the reason why we don't need to specifically require additional argument of this reference to the guard. Okay, so far at the high level, the push and pop functions need to do something that is related to garbage collection, and that is protecting the lines of code with the guard, which delimits the beginning and ending of an active state, and it is also delimiting the beginning and ending of the active state using the guard. And furthermore, instead of freeing the head pointer immediately, we are default destroying or retiring the head pointer at this point of time. So they are the differences from the traverse stack algorithm without garbage collection with traverse stacks algorithm with an epoch-based reclamation. Now you can see that that's all. That's everything I needed to discuss using this stack, except that they are explaining a few types. The stack is an atomic pointer to the node, and node contains an atomic pointer to the next node here. So atomic is basically a type that can be concurrently accessed. So this is the pointer value that can be concurrently accessed by multiple threads. So that's the purpose of the atomic. And it differs from owned because owns means the owned pointer. No one else is accessing this pointer at all. So that's the reason why we are creating a new heap object at this line of code. And furthermore, there are still a different type of pointer that is shared. So this head is the result of this load function, and the type of this head must be shared. A shared pointer is basically a reference to the global memory. So this shared is local. You can think of you can safely assume that this local pointer is a shared pointer is local to a thread, and when a thread reads the global memory, when a thread reads a pointer from the global memory, then the temporarily the pointer is stored inside the stack, and this shared is meant to hold the pointer to the global memory. So there are three types of pointers: atomic, that can be concurrently accessed; owned, which is an owned pointer to the heap object; and the shared pointer, that is temporarily holding the pointer to the global memory. And this API is designed in such a way that you can not easily break the rule of the epoch-based reclamations, and you can see that by reading the document, the two documents I presented at the beginning of this video. Now let's move on to the queue. So queue is a little bit more difficult than stack, but regarding the garbage collection, they are not that different with the stack. So the push function is also creating an owned pointer, and you're immediately turning it into an owned pointer and access the shared memory by passing the guard here. So guard is given as a reference because, and as a result, you can be quite sure that this push function is executed inside an active state. And as a result, you can safely load the temporary pointers to the stack. So as a result of this load, you can get a shared pointer, which is temporarily holding the pointer to the current concurrent memory. And blah blah. So there are so this guard mandates that all the accesses to the concurrent memories are executed inside the unactive state, and so far so good. And as usual, the push is not very interesting regarding deallocation because the push function doesn't deallocate anything. On the other hand, this pop function is a little bit different. So it does the same thing. It is given a guard, which proves that this try pop function is executed inside an active state. And using this guard, it can load the concurrent memory pointers in order to traverse to the next pointers. So far so good. And what is interesting is the same here. If you successfully update the head pointer, you effectively detached the first node from the queue, and as a result, you need to deallocate it at some point of time. And instead of immediately deallocating the pointer, we are going to defer destroy or retire this pointer in order to wait for the other threads to finish accessing the same node. And after calling defer destroy, we are reading the pointer value and returning the value here. So that is basically what's going on in this stack, and it is pretty much the same with the stack regarding the garbage collection. You protect the functions with a guard, which proves that the function is executed inside an active state. And furthermore, you defer destroy or retire the blocks instead of immediately freeing it. The same at all. And there is a little bit funny things here. So here in drop function, you are trying to pop the values until the queue is empty, and this function must be called inside an active state. So here we are going to give a guard to that, But the guard is an unprotected guard, means that, oh, even though even though you have a guard, you are actually not inside an active state. But this is actually correct implementation. At first glance, it may seems like wrong, but it is actually correct because at the time that queue is deallocated and at the time that the queue is dropped, you are quite sure that only you are aware of this queue. No one else, no threads else are trying to access this queue at all because they lost all the reference to the queue, and that's the reason why this drop function may be called for the queue. So you are the only one that accesses the shared the nodes inside this queue, and as a result, you don't need to protect your accesses at all. That's the reason why we are going to call unprotected instead of the pin. And this unprotected function means that you're not actually inside an active state, but I will give you a guard regardlessly because you need it. But still, it's safe due to the exclusive nature of this drop function. Okay, so far so good. And list is also the same. You are given a guard, and like as usual in the drop function, you are not going to need a guard, the real guard that signifies the active state. And here you're having many things, and the same thing happens. At the beginning of iteration, you need to get a guard by pinning it because you need to protect your traversal. And at the end of the traversal, you need to drop the guard in order to mark the starting of an inactive state or ending marking the ending of the active state. The same thing happens for the rest of the code. And for homework 5, you're required to implement a few data structures and that collectively implements the concurrent hash table. And I hope that you now understand how to do that, how to protect the deallocation inside the concurrent hash table. When you begin the access to the concurrent memory, you create a guard by pinning it, and after you finished accessing the shared memory, you drop the guard, which effectively calls the setQuestion function. And only inside those the active state you can safely dereference or reference the shared memory. And if you want to deallocate a node, then instead of immediately freeing it, you need to default destroy or retire the block in question inside an active state. So that is basically the higher level recipe for protecting data structures using epoch-based reclamation. And I hope that you now quite well understood how to do that for concurrent hash table.